In the last module, we talked about anomaly detection via isolation using the isolation forest, which is kind of the equivalent of a random forest for anomaly detection. We have seen that this is a very versatile method that performs relatively well even in moderately high dimensions. However, when we switch over to really high dimensions, as for instance we have in the domain of images, then the only techniques that really are promising are deep learning techniques. I guess you all have been waiting for the moment that we finally start talking about deep learning models, and here we go. So now we're going to talk about anomaly detection via reconstruction. And the idea is here to learn two models. One that is able to compress data into a lower dimensional space, and one that is able to reconstruct the data from this latent description. If we are able to fit these two models very well on the nominal data, then we can infer that whenever we see a high reconstruction error, then it is likely that we've encountered an anomaly. So let's review the idea of an autoencoder. So on the right, you see a schematic representation of an autoencoder. It consists, as I said, of two models. First of all, an encoder, which usually comes from a parametric family over which we can optimize later on. Similarly, the decoder, which also comes from another parametric family and which maps from the low dimensional space back into the original space, for instance, the space of images. And then finally, this system is trained to minimize the reconstruction error on the distribution of the nominal data or on our data set. So basically the error signal that we're going to work with is the difference between the original input and the output that we get whenever we first put this input into the encoder and then back again into the decoder. So meaning that we're going to train exactly for this kind of loss. So typically we are going to choose neural networks in order to represent our parametric families of encoders and decoders. And in the next lesson, we're going to do a quick recap on what a neural network is and what kind of architectures we can use for such autoencoders. All right, let's have a short recap on neural networks, since they are very well suited for finding no-dimensional representations of data. So I guess you all know that neural networks are built from artificial neurons, which get a certain number of input signals. They combine them and then push them through an activation function. More precisely, the input signals get combined via a weighted sum of the signals plus a certain bias factor, and then they get pushed to a nonlinear function, usually denoted as sigma, where sigma can typically be things like the sigmoid function, tanh function, or also very popular are ReLU or leaky layer. These artificial neurons are then assembled in layers which compute transformations from R to the D to some other dimensional space. Typical examples of such layers are convolutional layers. This is something that you see on the left here. For a convolutional layer, the neighborhood of each point gets convoluted so that the new value for this point or this feature will be an aggregation of the values that you find in the neighborhood. Similarly, a pooling layer also takes a neighborhood into account, but usually combines it or aggregates it into a single value, so having an implicit dimensionality reduction in the mechanism. And finally, fully connected layers, I guess you all know them, where we connect every input with every possible output, which is the standard layer architecture for neural networks. So this is also what we are going to use in order to build our autoencoder. As I said, we want to map the original data into a lower dimensional space while maintaining as much information as possible about the data within the data distribution. So convolutional layers are very well suited to build such dimensionality reduction mechanisms, especially on images, So here we see the schematic of applying a 2D convolution followed by a 2D pooling. Here you see you can parameterize the convolution so that the output will have exactly the same dimension as the original space. And then we apply this 2D pooling in order to aggregate whole boxes into single values, which gives us the dimensionality reduction that we're looking for. Next, we are going to connect this idea of autoencoder with the probabilistic approach that we talked about in the very beginning. The variational autoencoder is a very important special case of autoencoders, which incorporates the idea into a probabilistic framework. We first start off with a generative model, which contains a latent space and a simple distribution defined on this latent space. And now images get generated by first sampling in the latent space and plugging the result into a complicated transformation which outputs a corresponding image. We are going to train the generative model jointly with a model which is able to identify the area in the latent space where a given model originated from. Plugging these two models together gives us the shape of the autoencoder that we already know by now. So we can basically plug in an image, we get the area in the latent space, and if we sample from that area, ideally all the outputs should look like very similar to the input that we've given. To summarize, we first define a generative model using latent variables, and then we combine the maximum likelihood estimation for training this model together with posterior estimation through amortized stochastic variational inference. Plugging then these two models, doing inference and the one for the generative part, together gives us the variational autoencoder. Okay, let's start with defining the generative model. First of all, I said that we want to have a simple distribution in the latent space. So we're going to model the distribution in the latent space to be just a standard normal distribution. And then we need to define the conditional of X, so the image, given its latent representation. Again, we are going to model this as a normal, where the mean is given by a neural network that gets the latent representation as input. Note that we've chosen the covariance matrix to be the identity here. So this is not strictly necessary. You could even demand that the variance is much lower than 1 for your case. The reason why we model this as a Gaussian and not, for instance, as a Dirac distribution is that we want to have support of the entire space for the distribution that we define. But the variance, let me say that again, is not super important in this case. So as I said, we do not want to train this generative model alone, but we want to train it jointly with an approximation of the posterior of the latent space given an image. So for that, we are going to use variational inference, meaning that we also need to define a posterior model for this setup. And in this case, again, we assume that the shape of the distribution in the latent space given an image is again approximately Gaussian. And we use two neural networks that output, given an image, the mean of this distribution and the covariance matrix of this distribution. In case that you are not familiar with advanced Bayesian techniques for training neural networks, you probably wonder by now how we do the training. So the true posterior with respect to our generative model is something that we cannot compute directly because it's too expensive to compute it, but nevertheless it is defined by our generative model. So now let's have a look, how does the KL divergence look like? It is defined in this case as the expectation over the data distribution and the posterior distribution, our Q of Z given X. And then it's the log ratio between our posterior approximation and the true posterior with respect to our generative model. So as I said, the large problem when I want to compute KL divergence is that the second part, this posterior with respect to our generative model, is something that we cannot compute. However, there is a nice little trick, because if we now start decomposing all these terms that we see here according to Bayes' theorem, like this, and then use the log and some computation rules. Looking at this equation, it might not be directly apparent that this is very helpful, but look what happens if we rearrange this equation. So basically bringing the KL divergence to the right side and this term to the left side, we end up with something which we call elbow or evidence lower bound, which is defined exactly as our expected evidence minus the KL divergence, which is of course then the same as computing the expectation down below. However, it seems that we haven't done much, but taking a good look at this equation, we can directly see, since this is a constant, we can see that maximizing the elbow is actually equivalent to minimizing the KL divergence. So this is an equivalent objective. But looking at the second equation here, we can see that now only terms appear that we can actually compute. So we have directly the posterior approximation model, we have a direct model for the likelihood, and we have specified the distribution in the latent space to be a standard normal. So now using sample, we can estimate this expectation and use stochastic optimization methods in order to optimize the KL divergence. So as a recap, maximizing the elbow with respect to the parameters in Q is equivalent to minimizing the KL divergence between P and Q. And maximizing the elbow with parameters in P can be understood as raising the lower bound for the evidence. So this way of training enforces that the two models get aligned during the procedure. This concludes our lesson, so let's move on to the exercises to see how this works in practice. In this exercise, we are going to work with the MNIST dataset, and more precisely, we are going to try to identify corrupted images within the dataset, which we injected by our own. So please work through the cells. There won't be any coding exercises. It's just about observing the behavior of the models, and we see each other again with the solution. All right, so let's see what was in the notebook. First of all, after loading the data and doing a little bit of pre-processing, we're just doing like the minimal stuff that we need to do here right now. Now it's not about getting the best model in the world, it's about understanding how they behave in general. So we went over to inject the corruptions into our data set. And here you see a few of the examples that we injected. First of all, we cut some parts of certain images. Another corruption that we did is we introduced some noise into the images. We also have some images that were basically flipped to the side. Unfortunately, there's none in this visualization, but these three kinds of corruptions are what we want to identify. Of course, without telling the model that we corrupted the images in this way. We are going to use the autoencoder architecture that we have just learned about. More precisely, we are going to fit a variational autoencoder. Let's first review the encoder and decoder architecture that we are going to use. We are going to be rather straightforward here. So what we are going to use is 2D convolutions 2 times, then flatten the remaining input, use 2 dense layers, then output the mean and the standard deviation for the distribution in the latent space. Similarly, the decoder does the whole procedure in reverse. So we first push the input to 2 dense layers, and then we use the convolution 2D transpose as modeling something like the inverse of a convolution. So both models have around 200,000 parameters, 220,000 for the encoder, and about 260,000 for the decoder. We trained this model for 30 epochs on the contaminated MNIST datasets. So from the numbers, this looks relatively good. Let's take a closer look at the result. So in order to explore the latent space, we first pre-process it a little bit by applying a PCA. So we rotate everything so that we have the variance aligned with the axis. In theory, we have trained our model to have a Gaussian distribution in the latent space, so a standard Gaussian distribution, which should not favor any of the directions. Nevertheless, since we just trained an approximate model, we will still find certain directions in which there's a little more variance than the other, and it's still likely that we find in this direction also semantical properties encoded. So that's the reason why we do the PCA. So having done that, and now basically starting to walk around in the latent space, you can see images like that. I think I should explain this a little so that you understand what you are looking at. So in this case, we have a three-dimensional latent space, and we have fixed one of the components, in this case the second component, which we set to 0. And here all these images are generated by switching the value in the first two components. So, and I think you can now see quite impressively that this network actually learned to arrange all the numbers somehow in this three-dimensional space. So you can see that in the lower left corner here we have 5s encoded. On the upper right corner you can see 3s. The 8s are somewhat in the middle because I think this is a good number to transition to other numbers, so it's not very unlikely that they are placed in the middle. And you can do, of course, the same thing by fixing one of the other components. Now, in this case, we have fixed the first component, and we are moving in the second and the third component. And again, we find the 9s are encoded somewhere. And here we can find 8s again, and I think you can see the nice transitions between them. Finally, by moving in the remaining two directions, we can also find the 1, the 2s, and the 0s. Another way to explore the latent space is by playing with these widgets. In this case, I can directly set the x, y, and z component and can see how the image changes as I change the sliders here. So for instance, by lowering the first component, you can see that at some point it starts to become 3-ish. In the other direction, it looks more like a 9 or a 4. Here we get a pretty clear 3. Seems to be encoded in this direction. While here we have the 9s again. And of course, you can look at all possible combinations of these sliders. And you will see that you will find like different variations of the numbers, different numbers. You can really nicely see how they are arranged in the latent space. Here, yet again, another visualization. Now we've took a lot of numbers and encoded them in the latent space, and the color encodes the number that we got. So first of all, you should observe that this latent space approximately really has the shape of a standard Gaussian. So we would expect this 3D blob here, and this is really like rather well fit. And you can also see that it clustered all the numbers in different regions of the latent space. This is exactly what we saw when we were walking through this latent space. Finally, we can have a look at how the anomalies are mapped into the latent space. And it might be slightly disappointing because maybe if I would have asked some of you, probably some would have conjectured that anomalies are also anomalies in the latent space, so that they are not right in the blob, but somewhere mapped to somewhere outside. This is unfortunately not the case. This time again, we have mapped a lot of numbers, also corrupted one, and mapped them into the latent space, and mapped them into the latent space via the encoder. And now we've only colored the anomalies with colors according to the type of anomalies that we had. And here you see, unfortunately, there's definitely nothing that gets mapped into regions of low density with respect to the standard normal. This might be unintuitive in the first moment, but please keep in mind that when we reconstruct these images from the latent space, then they will probably no longer look like the corrupted images, but just as normal images. This is really why the reconstruction error will most likely work as an anomaly detection method. So this is what we can see here. So here we took a couple of numbers and mapped them into the latent space and then reconstructed them again and measured the error. I think you can see that this reconstruction is not perfect, not even for real inputs, for real numbers. For instance, here you can see this 4. This 4, when we map it to the latent space and reconstruct it, it looks much more like a 3, right? Nevertheless, if we take a look at the reconstruction error, then we see it's around 58.6. And now let's compare that with an image that really got corrupted. And this is one that we find here, for instance, here in this 3. We injected noise to this 3. And now if we reconstruct that again, he's not able to reconstruct this noisy image, but we get something that looks like a 5. And we can see that the reconstruction error is significantly higher, or even the highest number that we have among all these. So what's left now is to start the evaluation. We had prepared the code for you. And then going to the ROC curve and the PR curve, we can see that this is definitely a more challenging example. The ROC curve looks pretty rather solid, but in the PR curve, we can already see a certain kind of degeneration. And you can even see that there's like quite a significant drop, just around 60% recall. Given that we know that we had exactly 3 types of anomalies in our data, and looking especially at the PR curve, it might be a natural guess to say, okay, maybe it was the case that we got 2 of the corruptions rather well, and 1 maybe not so well. So let's check if this is really the case. So again, we map a lot of images, encoding and decoding them, and then we order them by the top outliers. And I think what you see here is pretty clear. So the anomalies that we definitely best recognized were the noise injections. So you can see these, like the top anomalies are mostly these noise injections. You can also recognize the transposed images that we introduced. We have quite a few here. But as you see, there are almost none. Here's one image where we cut the upper half. But besides that, there's almost none of them. But we can see that it also recognized a couple of the normal images in the data set. And yeah, at least for me, it looks like that some of them are fair to be counted to be natural anomalies. For instance, here you see the SIG6 or the SICA8 here. Also, these 4s are like relatively untypically drawn, for instance. So here you can see that we were able to identify some of the corruptions very well, one of the corruptions not well at all, and we have gotten some things that we didn't expect to get. So this is, of course, matter of discussion, whether we are interested in them or not. And some applications we also might be interested in these natural anomalies, and some maybe not. So as a recap, we were able to identify 2 out of the 3 corruptions that we injected rather reliably. We also found some natural anomalies. And of course, it's up to the downstream task whether we are really interested in them or not, maybe not. I hope that showed you that deep learning methods can be very powerful for anomaly detection. However, it is often hard to predict which kind of anomalies they will identify reliably and which not. This concludes our 4th module of the workshop, and we leave the part where we look at particular methods for anomaly detection and rather take a focus on different application areas of anomaly detection. In the 5th module, we are going to talk about anomaly detection on time series.